but you need to root to get into the directories.
Okay. Yeah, so sorry about that. It's always fun when you're trying to compromise and find something that works for everybody, and usually it ends up working for nobody in the end. But, so this workshop is going to be about stack, buffer overflows, and a little bit about format string. And exactly what we cover is somewhat dependent on you guys. So this is shamelessly ripped off from a class I did for Pentester Academy that is available. This class is actually completed. It's one of a series of classes on reverse engineering stuff. So this is a 32-bit Windows reverse engineering class. If I remember correctly, there's about 19 hours of stuff in this class. So it's a pretty deep dive into that. It's not just stack buffer overflows. It's like pretty much everything. So this is sort of the beginning portions of that class in a workshop format, depending on what you guys want. And where we get time-wise, we'll also talk about format string errors. This is another flaw in software. So first of all, question, how many of you have done any kind of reverse engineering before? Okay. How many of you have done at least a little pen testing? Who feels like they completely understand all these flaws in software and they're not sure why they're sitting here? Anybody? Did you get it to work?
Yes. I'm still copying, but
I got a copy.
yeah, I just copied it. I should be
Cool. Okay, so just a little bit what we're going to talk about. We're just going to start talking about, how do you get started with this? What sort of software do you need? Hopefully, at some point, you guys can get a copy of a little Windows 7 OVA file that's on the thumb drives that some of you can read. And also, it might be available soon on a web server near you. So we'll have to stand by for that. And the nice thing about that is a lot of the tools that you would need are already installed on there. We'll talk a little bit about assembly. Any of you know assembly?
Max assembly.
No.
Yeah.
Kind of
old. We're going to kind of hit on the basics. And again, this class came from a class at Pentester Academy. Pentester Academy has several classes. I mean, not just several. They have a lot. Like 40-ish classes, I think, right now on things like assembly. So in that class, of course, I just sort of refer people to the other class. Not that this is a promo for Pentester Academy. How many of you are familiar with Pentester Academy?
Heard of you guys?
Yeah. The short synopsis, Pentester Academy is a subscription site, $39 a month to get access to every single class they have. So they have some ongoing classes, and then they have classes like the one that I extracted this stuff from that are, like a capsulized class. It was at one point an ongoing class until I finished it. But we got new stuff coming up all the time. A lot of people ask me, hey, I want to get into InfoStack, what should I do? And it's like the biggest no-brainer ever. $39 a month to get access to like everything you need. If you need to learn Python or refresh your Python, there's classes in that. 32-bit, 64-bit assembly, wireless security, Metasploit. It's probably there. So anyway, if you're not familiar, go ahead and check it out. You can actually see all of the courses and videos that are available without subscribing. You just can't watch all of them, but you can see what they are and get a feel for what's out there. So we're mostly going to talk about stack overflows today. We'll start talking with a little bit of theory of stack buffer overflows, and we'll talk about how do you locate them. What we'll find is that you often need to calculate some sort of an offset. Basically what that means is I found a place in some code where I can inject my bad stuff, and I need to figure out how far into the stuff I'm injecting I need to start my bad stuff. So there's some methods for doing that. Talk a little bit about some exploit techniques, and then we will shift to talking about some protections that are coming out or have come out that make this harder. If we were talking about Windows XP, it would be easy. If I wanted to wuss out, I would have just given you a Windows XP OVA and it'd be like, hey, look at the Stack Overflow stuff. This is super, super easy, and you don't have to do anything special. Right? But I do want to spend some time talking about some of the protections that compilers and operating systems have today against these flaws. They've been around for decades. And then we'll, at the end, also talk about format strings. And the thing about format string errors is that this is something that is agnostic somewhat to the operating system. Now, it turns out if you have a Linux box and you took some of the programs that we might use it as an example for this section of the class today, and you compile them, GCC is an awesome compiler. It'll actually give you a warning like, hey, there's a format string vulnerability on this line. You probably shouldn't do that. And it'll do similar things to protect you from stack buffer overflows. So you actually have to work harder to make a vulnerable Linux app than to make one that's not, which is a good thing. Okay, so just a little bit, talking about reverse engineering. What is that anyway? Reverse engineering, this is my definition, or reversing, is just the art of determining how something works without access to the original design specifications or code. And there's a lot of reasons that you could do reverse engineering. You could do it for finding flaws. That's kind of what our focus is today. You can do it if you're trying to clone somebody's stuff. Right? Maybe you're an evil businessman from China. I don't know if anyone heard the FBI person talk yesterday. They want all your IP, all your intellectual property. You can also just do it because you're trying to understand how stuff works. Or you can do reverse engineering to try to mitigate malicious programs. You're trying to understand malicious programs, malware basically, in order to figure out how to protect against it. So in terms of getting started, you're definitely going to want some sort of debugger. Now you can do reverse engineering with some of those standard debuggers like GDB out there, but they're not really meant for this kind of work. Those are meant for, hey, I wrote a program, I have the code, and I want to know why my program doesn't work. I mean, you can do this work with it, it's just, that's not what they were made to do. So in the world of reverse engineering, the debuggers out there, one of the debuggers that gets used a lot is IDA Pro. Who's heard of IDA Pro? Good product, right? Is it cheap? No. That's its biggest downside. It's not a cheap product. There's some free alternatives. There's something called Immunity Debugger. We use that a little bit. There's another one called OllyDB, which is about the same thing. You probably want some sort of virtualization. So you want to run Windows if you're doing Windows software, which is what we're doing today. You can say, what version of Windows do I want? We're going to use Windows 7. You could use older versions of Windows, and that's easier. If you go out and you look for shellcode and other things for Windows, You look under Windows XP, and there's all kinds of stuff. Well, it's not just because Windows XP's been out there longer. It's because it's a lot more vulnerable. That's the other part of it. So you want virtualization for running Windows stuff, because I always have Linux as my base. Isolating suspicious stuff. If you have some malware, you're like, hey, don't run that on your regular box. So normally you're going to want to install some tools. The OVA file has them pre-installed. Some scripting tools, of course. Python 2 and 3. Python 3 is starting to come with a lot of Linuxers now. It used to be that only Python 2 was pre-installed, but I think some of the recent versions of Debugging and Ubuntu come with both. Bash scripting can be helpful as well. On Linux, if you're doing this kind of stuff, there's a package called Build Essential, which you probably need to install. It has compilers and things like that. I always wondered why it's not called Build Essentials. I don't know why it's not. It seems like it makes more sense to me because it's really a bunch of things. It's not one thing, but I guess it's the Build Essential package. I don't know. If you start getting into this, you probably want to install things like fuzzers. You don't want to know what a fuzzer is. It's just something that will vary the input to a program in order to try to find a flaw. And this can help you find flaws initially and make your life a little simpler. And there are different kinds of fuzzers out there. Some of the applications we're going to look at are simple in that they accept command line parameters, and you can overflow those. Not too many programs out there that you're going to actually try to crash and do other bad things to work that way. They're probably going to accept stuff over the network. You can easily translate what we learned today into that kind of situation. So there are network fuzzers, command line fuzzers, different kinds of tools out there for that. So of course you're going to need a compiler in some sample apps. We also have programs called decompilers. Decompilers try to take a binary and go back to C. Almost everything in the world is at some level written in C. You might use a different language. That compiler was probably written in C. The operating systems are all written in C. So decompilers have different levels of complexity and different levels of success in going from a binary to C code. So that's the kind of stuff that you'll use as well. So some of the debuggers out there, OllyDB, what's good about it? It's free. It's pretty lightweight, somewhat customizable. Biggest minus is only works with 32-bit Windows apps, doesn't do 64-bit, not really updated, and it's free. There's no support. There's immunity. Immunity, same pluses. One of the nice things about it is it has a little Python scripting engine, and you can write your own Python scripts for it, and some people do. And of course, biggest minus, 32-bit Windows only, and no support. Then there's IDA Pro. IDA Pro is a great product. There's entire books on it. I was at Black Hat this summer doing a little training on, what was I doing training for? I think this summer I was helping out in the PowerShell class. Last couple of summers I helped out in the wireless class. But, this is the gold standard. If you're a professional reverse engineer, you probably use an IDA Pro. I know at Black Hat they had like 2 classes, like a 2-day getting started and then a 2-day advanced class that you could spend a lot of money on. IDA Pro supports a ton of platforms. You can do 32, 64-bit, Windows, Linux, Mac, I think ARM. I mean, they support a lot. I think they start at like $3,000, a year per seat, something like that. So you have to be committed to doing this stuff if you're going to buy item. There is a free version. It has less platforms. Up until recently, it was one platform, 32-bit Windows. And of course, you don't get any support. But there is a large support community because it is very popular. It's a good program. Okay. So, quick review / introduction to assembly. So if you want to learn how stuff works, I'd say learn assembly, at least at a basic level. Like, you don't have to be God's gift to assembly programming in order for this to be useful as an exercise. But, knowing assembly kind of helps you know how stuff works. So when it comes to this kind of stuff, the biggest thing that we need to know about are things like registers and the stack. So can anybody give me kind of a basic definition or just tell me what the heck is a register anyway?
It's a place to put something.
It's a place to put something, right? Where does it physically live? On the CPU, right? So on the CPU, stuff is fast, right? You're running at, let's say, 4 gigahertz or so on the CPU, and you've got multiple cores nowadays, and you've got caches on the CPU because everything on that little chip is super, super fast. As soon as you get off that chip, whoa, it slows down a lot. Now you're talking about megahertz speeds, not gigahertz speeds, and you have to play with other people, right? If you're on the chip, you don't have to deal with anybody else taking up bandwidth. So all these CPUs will have high-speed memory areas called registers. So if you're talking about a 32-bit CPU, there's 32 bits wide. 64-bit CPU, they're 64 bits wide. It's one of the distinguishing features between 32 and 64-bit. So, these registers, these high-speed areas, there's 3 of them in particular that we will look at quite a bit. One of them is called EAX. Just a little bit about naming conventions here. The E stands for extended. So before there was 32-bit processors, there was 16-bit processors. So in the 16-bit processors, the original 8086, for example, you would have a register called AX. It was 16 bits long. Then when you came out with the 32-bit processor, the same register is called EAX, the extended AX register. Sometimes the A register is called the accumulator just because it is used a lot. It's like the hardest working register. Some of you might have seen a show. It's a really old show now. I shouldn't even mention it. Living Color. Anyone ever see this show? It is time for Hey Man with the Headleys, the hardest working Jamaican family. You guys remember that skit? It's like, how many jobs do you have? I have 10 jobs. So, the accumulator could be in the Headley family. Right? Hardest working register. Used a lot. So, the accumulator, the A register, AX, meant the whole 16 bits. You could also address each byte separately as AH, the high byte, AL, the low byte. And that exists even today. So you can still refer to EAX, the 32-bit register, or AX, just the lower 16-bit, or AH, or AL. Right? And now, if you go to 64 bits, then they just call it R. They're like, the really, really big, really extended, I don't know. So that's something you'll notice when you look at debuggers. All these, like, why does every single one of them start with E? That's why, in a 32-bit. environment.
So it's RAX in 64-bit or just split R?
RAX.
Okay.
Yeah.
So just
Because
place
the R is the prefix that just says, hey, that means all of it.
Okay.
Yeah. So these two, SP stands for stack pointer. So we'll talk a little bit about the stack and why it's important. And BP is something called a frame pointer. So if you look, when we look later at a debugger, you'll see there's different registers, and you'll notice that there are a couple of them that end with P, and some of them end with D, I, or I, and then there's ones that just end with X. But these are the three most important ones, and there's some others out there as well. So we'll talk about the stack and how that's important. And when we talk about all this stuff, we'll also need to talk about calling conventions. When I call a function, how does that work? How do I pass arguments to and from a function? And I need to understand these three items in order to understand stack buffer overflows. Okay, so calling conventions. How are we passing things to our functions? There are three common calling conventions on the Windows platform. And the first one is called cdecl. C, the language, declare, basically. So this is pretty standard. This is what is used by default for C. And how does this work? You call a function. Maybe it has two arguments. You push them on the stack. So you guys understand what a stack is, or do we need to talk about that? It's okay if you don't. Probably should? Okay. So a stack is a data construct where it's called last in, first out, LIFO. So you can think of it like a stack of paper, if you will. If you want to add something to the stack, you push it on the stack. You push it on the top, and then if you want to get it back, you pop it off the top. So if you look at assembly, you'll see push this onto the stack, push this onto the stack, and then you'll see pop, and then of course you have to reverse the order, and you get your stack back. So that's, in a nutshell, what a stack is. It's just a place you can store stuff, and you just push it on, pop it off. So there's a notion of the top of the stack. In cdecl, the caller must clean up the stack. So what does that mean? I want to call a function. That function takes two arguments. I take those two arguments and I go push on the stack, call this function. Function returns. Then I have to pop the stuff off the stack. That's cdecl. Okay. How do they put these things on the stack? They push them on the stack from right to left. That's the order of things. Now, why might I use cdecl? If I have a function that takes a variable number of arguments, a great example of that would be printf. I should have asked, how many of you know at least a little bit of C? So printf is a pretty standard function in C. It allows you to print stuff out. If you're doing Python, you do just print. A lot of other languages, it's just print. But printf is used to print stuff out. What we'll find out later, and this comes into play when we talk about format string flaws, is that printf will take one argument, or two arguments, or a whole bunch of arguments. So one of the things you can actually specify as this first argument is a format string. It says, hey, I'm going to pass you a bunch of other stuff, and this is how I would like you to print it out. Then there's the lazy way to call it, where you just say, I wanted to print this one thing, so just print that one thing. And that's a problem. what we'll talk about toward the end of our workshop time today. So that's why, one reason why we have Debugger. You might say, why don't we just use standard call for everything? Well, because we can't. Now, standard call is the standard calling convention for Windows 32-bit API calls. So API is Application Programming Interface. So if I want to write a Windows app, I write a little bit of code, and I mostly call a lot of API calls. Pretty typical. Here, the callee cleans up the stack. So I just push stuff on the stack, call my function, and then it returns, and I don't have to do anything else. It's easier for me to program with this. Same thing, arguments pushed on from right to left. You can't use it, though, with things like printf, because the callee has no way of knowing what you pushed on the stack. It's a variable number of arguments. How would I know what you put on there and how big things are? And, you know, if you talk about C, if you've done any C programming, you're like, you give me a pointer. Do I need to free the space that this pointer points at? I don't know what to do. So I'm not going to do anything. That's standard call. Then there's fast call. You don't see this used very much. In 32-bit Windows, you don't see this used very much. When you start talking about 64-bit programming, you will see this used a lot. And actually, if you look at ARM, this is sort of the standard thing for ARM. ARM doesn't use the stack in the same way that we're going to use it here. Just a little tease. I'm doing a whole series of reverse engineering courses at Pentester Academy, and right now I'm working on the ARM class. So first thing I'm going to put out there is an ARM assembly class, because nobody knows how to do ARM assembly. It's a little bit different. It's a little weird. And then there'll be an ARM reverse engineering class that comes out very quickly. Okay. So there's a stack buffer overflow. I want to exploit it. What do I need? What are my necessary conditions in order to do this? You know, often you want to say, what has to happen for something bad to happen? Well, you have to have maybe all three of these conditions. So, for example, anyone fly helicopters? A chopper pilot. Okay. So, when you're flying a helicopter, there's something called settling with power. It's kind of really bad. Like if you come in to land your chopper, and you keep adding power, you sink faster and faster and faster. The more power you put in. It's not a good thing. But there are three conditions that all three of them have to be there in order for this to happen to you. Right? So you remove one of the conditions, and it's not going to happen. So to get a successful stack buffer overflow, you have to be able to overwrite the return address on the stack. And we'll talk a little bit more about the stack here in a bit. But when I call a function, the place I was in memory, in my program, that location, that return address, is stored on the stack. I need to overwrite that address. So to say, go somewhere else. That is at the heart of all stack buffer overflows. Well, I shouldn't say that. Most. I don't like to say all, because usually there's some weird case where that's not the case. Usually, but not always, you might inject your shell code on the stack. Now, if you want to learn how to write your own shell code, guess what? There's actually a class at Pentester Academy about that. You can also just download other people's shell code from places like Shellstorm. Never heard of Shellstorm before. It's a nice little site. And you can just say, I want a payload, some shell code to do this on Windows XP. And if you look, you'll see a lot of stuff for Windows XP, Not as much for newer versions of Windows. By the way, speaking of newer versions of Windows, we have Windows 7 that we're going to use here. Some people are like, whoa, why don't we use Windows 10? Truth is, when you look at forensics, there's not a whole lot of difference between even Vista and 10. Most of the differences between Vista and Windows 10 are just in the user experience, not in the way it fundamentally works. Yeah, sure, there's more things in the registry, and there's more stuff on the file system that you can stack. But fundamentally, it's the same. So if you can exploit a flaw on Windows 7, you're probably going to be able to do the exact same thing on Windows 8 or Windows 10. Okay, the stack. Let's talk about the stack. The whole goal here is I want to overflow some local variables. And here's why this works. If I look at the stack actually grows downward in memory for Windows and most operating systems, actually. Windows, Linux, Mac, they all work like this. So when I push something on the stack, I'm actually putting it in a lower memory address. Now, I can push things on my stack, and how do I make space for things on my stack? I make space by subtracting from that stack pointer we were just mentioning. So if you look at code, you'll see subtract, 32 from this pointer. Okay, why am I doing that? I'm making 32 bytes of space. So what is in this space? I will have any local variables. Local variables are sometimes called automatic variables or stack variables in C. In C and many related languages, if I have an automatic variable, what does that mean? I said int x. I just made an automatic variable. That variable lives and dies in the curly brackets where it was defined. So I can actually have curly bracket, opening curly bracket, int x equals 5, closing curly bracket, guess what happens? It creates it and destroys it immediately. Nothing else happens. Puts it on the stack. There, then and gone. Well, all your functions, don't those live in curly brackets? They do, right? So any local variables from when you create a function, those will be on the stack. Following those, you will have the frame pointer. That's the EBP, not SP. And it says, hey, where do I end? My little frame, if you will, for this function. This function is storing certain things in the stack. Following that is the return address. When this function is over, where should I go back to? And that's the reason that is in red is here's what I can do. If I have a local variable that's not been properly constrained, I can overwrite it. Let's say it's a 2-byte integer. I can overwrite it, overwrite any other variables, local variables behind it, overwrite this frame buffer, and then overwrite this return address. Now, if I overwrite this return address, I can easily crash the program. That's the easiest thing to do. You give it some bad address, and it tries to go back there, and it says, whoa, I could not access this address. That's a problem. Depending on the version of Windows that you're dealing with, after you give it a new return address, you can also give it some shell code that you got either from Shellstorm or that you wrote yourself. By the way, I will say this. Once you start getting into this, you start to realize why it's so picky. You know, you run Metasploit. How many of you run Metasploit? At least familiar with Metasploit? And sometimes you run an exploit, and it works. Like, everyone's favorite exploit is what? MS-08, 067. Works almost all the time. Not all the time, but most of the time. Probably good 90, 95% of the time. I remember one time I was doing a demo, and it was one of the few times I'm like, exploit. I didn't hit a shell. You're like, oh no, what am I going to do? And some of my students are like, what are you going to do now? Exploit. Oh, got it now. Right. But the more you learn about these flaws in software, the more you understand why this stuff doesn't always work. Right now I'm teaching a pen testing class at the university, and you know, I remember one year I taught this class, and someone in their feedback at the end of the semester was like, stuff didn't work in this class. Like, welcome to pen testing. You know, stuff doesn't work all the time. Sometimes you got to try more than one thing. Why is that? Well, it doesn't take much to change the addresses involved here. Because typically the return address we're going to point to is right after that space in memory. So we need to know, where is that space on the stack when I ran this function? And there are things that I can affect that and change that. And that's one reason why a lot of these exploits are highly dependent on the exact version of the software and the exact version of the operating system that you run. So that's the stack. So this is, you know, a big player, especially stack buffer overflows. We're talking about first. Questions about this before we kind of move on? You guys feel like you get what we're talking about here? Sure. Don't be shy, because it's real important that you understand this, or you won't understand pretty much anything. You don't understand all this stuff. Okay. We will get into some of these protections a little bit later, but let's go ahead and try to do some actual hands-on stuff for a little bit, and then maybe we'll take a little mini break, because I know it's been almost an hour. Okay. So let me go ahead and run on over to this guy. How many of you have managed to get this OVA file? You got it running?
Yep.
Wow. You got the file, right?
Oh, yeah.
But you don't have it up and running?
It was, and now it crashed.
Oh.
Redoing it.
Well, it is Windows after all. So what I'm going to use for this is a little IDE, a little integrated development environment. It's called Dev C++. It's free. You can download it off of GitHub, I believe. I think it's GitHub. Just search for it, you'll find it. And it's pretty decent. So let me go ahead and bring up a program. Let's see if I remember. I didn't remember to grab it, did I? Oh, No, I did. Okay. So here's a very simple program. And what does it have? It has my main function. So I got my main function down here. It takes the standard arguments. Int argc, how many things should you pass to this program? argv is an array of strings for everything you pass to this program. I create a local string called local string, and I give it the value main function, and then I create a local integer, I give it this value, I call function, and I give it argv1. argv1 is just the first thing you passed in on the command. This function might make you think of something if you're old enough. Saturday morning cartoons. Might think you think of conjunction, junction. What's your function? Come on, don't leave me hanging. What's your function? Hooking up
It's been too long.
phrases and and words and something like I forgot it. It's Saturday morning. Okay, so my function takes one parameter, and then here's what it does. It has a local string, a local integer, and then it has another local string that has 10 bytes of storage. And here's the flaw, right here. I use stir copy. Now, stir copy, the way it works is the destination actually comes first, and the source comes second. So I'm saying, hey, whatever was passed in, please copy that to local string 2. But there's a problem. And here's the problem. Local string 2 is at most 10 bytes long. So if you know how C strings work, that means 9 characters plus a null terminator byte that has a value of 0. And then I return 1, and that's pretty much it. My function returns to main. Main returns 0. 0 means it worked. Anything that's not 0 means it didn't work. And I go along my way. Unless someone passes something into this program that is longer than 9 characters. As soon as they do that, this will overflow local string 2. Now, one of the questions we'll have to answer is, how far after local string 2 do I have to go till I hit that return address that we want to override? So that's the first question. How do I get this offset? How do I calculate this offset? Then the second question becomes, how do I know what to put in that new return address? And how do I get my code that I want to execute? Right? So that's kind of what we're going to work through today. Is we're going to start with this very simple program, and we're going to go from there and say, all right, I want to abuse this super simple program. So let's go ahead and, it's about 10-ish or so. Let's just take a quick break. See, it's about 10:05 or so. You guys can go get a drink and relax a little bit. And we'll come back at it, and we'll try to go through this. So you have a web server up?
I didn't. I can reformat this, though, and rewrite out stuff. That would help people.
Yeah, feel free if you want to format it.
Is he running? Anyone else? Your Linux?
We're running.
Okay. Does anyone else need it? Okay, well, what do you use? On a Mac? VirtualBox?
Yeah, I do.
I'll try to do a BFAT then.
Well, it's not going to work for FAT.
With Mac or VFAT?
Well, the file's too large.
Oh, okay,
The
I got
OVA
you.
file's too large.
That's okay.
That's the whole reason why.
I understand now.
You know, if you work in forensics, you run into these issues all the time, right? Because you can't just run FAT because FAT has a 4 gigabyte file size limit. Alright. So, have a little break. We'll see if we can get most of you up and going. If you can't quite get it up and going, I think we can still, you know, get something out of just following along a little bit.
Computer, I was telling you how to crown, so if I have
Tell it to stop.
Just hit the stop recording, will give me a resume.
And then number it once.
Okay, now we're good.
So here is our little program. As we said, pretty simple. You can go ahead and build it.
The last Oreo.
If you're doing this yourself, especially if you're doing it later. With this tool, make sure that you tell it that you want a 32-bit release. You could cheat a little bit, say 32-bit debugging, and it'll install some additional symbols, but you know, try to make it a little more real world. Where, well, I guess somebody might do a debug build of their tool and release it. I'm sure it's happened more than once where people forgot to do that, but I wouldn't expect that. So we go ahead and build this. Pilot, compiled in 0.45 seconds, and now I'm pretty much good to go. And let me bring up immunity. And I'll say I want to open a program, and I want to open this buffer overflow program, and here it is. Now I apologize, given the limited resolution that we have here on the screen. You know, stuff's kind of going off the screen, and it's not exactly ideal. But let me give you a quick overview of this debugger. Most of these debuggers that are used for reverse engineering work about the same. Over here we have our program. Over here we have our registers. Here we have a generic memory dump. And we can decide where we're going to dump memory. And over here is our stack. So we haven't started running it yet, so not much is going on. So if I look over here, you'll notice I have EAX, and it says buffer, overflow, module entry point. It's basically where it's pointing at this address. There's the A register, the B register, C register, D register. And you'll notice that all of these are pretty much, well, C and D are set to 0. My stack pointer says here's where my stack is at the moment. My frame pointer is not pointing to anything yet. And I have a couple other registered memory Don't worry about those. They're not important for our purposes. And we will see some other registers. One of the things that happened over time is that we added registers, and a lot of these are used for things like floating point processing. If you look at an old processor, it knows how to do add, subtract, multiply, occasionally divide. Some of them don't have divide. And it's just integer math. When you look at newer processors, they add in the floating point processor. And if you go back a ways in the Intel line to the Intel 386, I believe, was the last that didn't have a built-in math processor. So you could buy a math coprocessor to work with your 386 chip. But that's not so much the case today. But again, understanding this stuff doesn't really require you to have all that. Okay, so as far as debugging goes, you can step into things. This means if I call a function, I'll step inside of it, or I can step over things. And there's also some shortcuts, F7 and F8. So here I am in a bunch of library code, basically. You'll notice it says that I'm in the module NTDLL. I'm not actually to my code yet. I'll just step forward. I'll try. There we go. This laptop has one of those annoying features that requires me to actually push the function button. Okay. So here we are at the start of our actual code, and you notice the address 4014E0. That was what was stored previously in one of my registers, in the EA register. And now it's come to this. So this is my code. And there's going to be a certain amount of preambles in this code. And that's what's here. And then I have my functions. Notice that my functions have been grouped. See these little brackets, or whatever you want to call these? Here's my function. How do I know that it's function? Look at the code. Here I have a pointer to conjunction function. That was a local variable. We'll come back to this in a little bit. Here's my main. So it has some preamble code. And then I move some stuff around, and then I'm going to call my other function. So let me go ahead and just step. Here I'm moving some things. And now I'm getting ready to call 401EE0. 401 EE0. Step in. And now I'm going to add C or 12 to this. And I'm just going to go ahead and just run it, because I already have some breakpoints set for sake of time. I'm going to hit F9. And now I'm here at the start of my main function. So there's going to always be some preamble code. It's not terribly interesting, which is why I kind of skipped over it. And here we are. What's it going to do first? It's going to save EBP. It's going to say, please push that onto the stack. So over here's my stack. And notice it says return to this place from this place. So we got a return address. So we go ahead and step. Now I have EBP on my stack. It's set to 28FF88. So 28FF88. It's down here a little bit. FF88. Here's my frame. I'm saving that. Step again. I'm rounding ESP. And then I'm going to subtract hex 20 or 32 from ESP. So remember what we said, stack grows downward in memory. So when I subtract 32, I'm making space for 32 bytes of stuff. So now I've made my space. I'm going to call this function, buffer, overflow, blah, blah, blah. And then I'm going to set up these variables. So go ahead and do that. I'm just going to step over this call. You might say, why'd you step over that? That's more preamble code. It's more boilerplate code that I didn't write. What is that going to do? That's going to set up my ARMV and RC. So now, if I step over this, it has moved the address where I can find main function to this place on the stack, ESP plus 1C. So notice here on my stack, what does it say right here? Here's the address, 404015, and that address points to an ASCII string main function. Now I want to move my other local variable that contained the value 11223344 to ESP plus 18. Let's do that, see what happens. Now I have this value 11223344 right above this. A couple of important things. Intel systems are little-ended. You guys remember what that means? If you have a multi-byte value, the least significant byte comes first. Now this is being displayed as 11223344 because of the way I have this set. I have this set to display 4-byte chunks. If I looked in the actual memory, it would show up as 44332211. So keep that in mind. That'll be relevant later in our discussion. So now I'm going to move to EAX this location, 550F78. I'm going to add 4 to it. And then I'm going to move this value. So now EAX contains 0. And I'm going to call function. But before I do that, I'm going to have a problem. So notice it's going to call the 401500. Here's my function. What's the problem I'm going to run into here? Does anybody know? Let me just step ahead a little bit. I think you'll figure it out. Ooh, access violation when reading this address. What am I passing to function? argv1. There is no argv1. I didn't pass anything to this program, did I? I just said, run the program. And that's a problem. So here's what I need to do to fix that. I go to debug. I say arguments. Let me give it some arguments. And I'll just give it an argument right now. 1, 2, 3, 4, 5, 6, 7, 8, 9. I had 9 characters of space. Plus 1 byte for the null at the end. And I'll rerun it. And it's going to tell me, hey, you have to restart for this to take effect. Fine. Let me restart.
So that first example is just the program sort of crashing, and that's how the debugger sort of shows you that.
Right. I just want to kind of walk you through how do you do that. And we set a breakpoint. So now I can just say F9, and I'm going to go right to my actual code. And this time around, it'll actually work. So we'll go through this a little quicker. So here I am in my main function. And you'll see this XOR EAA, or EAX, not the Experimental Aircraft Association. With itself, that's a nice quick way to make something 0. XOR it with itself. And now we're going to move hex 11 to ECX, move ESP to EBP, push some things in the stack, load an effective address for this value into EDX. So all of this stuff here that you're thinking, oh, what the heck does this do? This is setting up my RV and my RC, basically. So let me go ahead and just go to my next breakpoint. So now, same thing. I made 32 bytes of space. Here you can see main function just showed up. Step again, and you see my value 11223344 showing up. Now what? I'm going to add 4 to EAX, and I'm going to move into EAX a pointer. This pointer points to what? This ASCII string, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's my argv1. Now I'm going to call buffer overflow of the function at 401500. That was its address. Go ahead and step into this. So notice my stack. I have just one function argument. Here it is, top of the stack. What is after that? An address. Let me call into this. F7. Now I'm in function. What's the first thing it's going to do? Save EBP. Push it on the stack, please. All right, let me do that. Now I see this value, 28FEC8, is on the stack. And if I look down here, I see here's another frame on my stack. which I've seen. I want to subtract hex 38. I'm saving a lot of space on my stack. And now I'm going to move conjunction function onto the stack. I say FA here is the EBP minus C. And where's my conjunction function? There it is. Right at the bottom of my display. And now I'm going to move dead beef. There it is, dead beef. What comes next? I'm moving to EAX, a pointer to 1, 2, 3, 4, 5, 6, 7, 8, 9. I step again, and now I'm going to move those values. I'm going to load the effective address of this. That's what LEA means. And all right, now I moved EAX that has this value to a FE7E, to a FE7E here, and now I'm going to call stir copy. Okay, so stir copy has as its arguments, first argument, destination. Second argument, source. Remember how those are pushed onto the stack. And notice that my debugger is smart enough to know that's the case. It says, oh, the source is this, destination is this address. 28FE7E. 28FE7E, which is kind of midway between these. So I'm going to jump over this, unless you really want me to trace through stir copy. It's not very tight. So we'll just kind of skip over it. Now what do I see here? I see the value that is stored as hex for the ASCII 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this looks a little weird for a couple of reasons. Number one, it's little ended. So remember, only half of this entry is relevant here. And it's the upper 2 bytes, because they come later. So it says 3-1, that's the ASCII code for 1, 3-2, 3-3, 3-4, 3-5, 3-6, 3-7, 3-8, 3-9. 0-0. There is my terminator, my null terminator. It's all good. Everything's great. Why is everything great? Because I didn't overflow it, did I? I exactly filled it. I didn't go further than I needed to go at all. So now if I just continue, what am I going to do? I'm going to move 1 to EAX. That's my return value. Remember we said return 1 from this function? And now I'm going to call leave. What does leave do? Leave fixes my stack. Yes, sir.
If you just flipped 1, 2, 3, would it still take up 3 blocks and just pad out with zeros? Like if instead of passing 1, 2, 3, 4, 5, 6, 7, 8, 9, you just pass the shorter
I believe it will not fill past the terminating line.
Okay.
And that was probably dependent on the exact version of stir copy in the library that's being run, but I think the standard Microsoft Visual C runtime library is not going to
It's not going to pad it out to that level.
I don't believe so.
Okay.
Well, let's think about this. For one thing, if you did this right, you should use stir end copy. But how does it know how much space is available? It doesn't know. So I guess we would never do that.
Okay.
I know it's still early. This is like day 2. Day 2 in a conference, you're always like, it should be obvious, but it's day 2 of a conference. I'm sure day 3 is not any better. By the time you get to tomorrow, you'll be like, where am I? Okay, so watch what happens here. Right now, this is at 28FE60. I'll call leave. And notice this changed. I can go back here. This is still here, right? All my values are still there. Here was my destination, which now points to the string. There's my source, my return addresses, etc. And now when I call return, it's going to say, all right, where am I going back to? I'm going to return back to here. So I'm back to my main function. Now what? Okay, so I'm back to my main, and I want to do this. Just step. I move 0, that's my return value. Again, I call leave and I call return. My function exits. I'm just going to hit go. It says process terminated, exit code 0. It's a normal termination. You guys still with me so far? So this is the regular, okay, it ran. It ran just fine. One of the things I said we're going to have to do is we have to figure out how far do I need to go to get to that return address. That's step number 1. Figuring out that offset. There are a couple of ways that I can do that. I can actually try to calculate it. Sometimes it's easiest just to run it and see what happens. Now, sometimes, depending on what you pass into a program, it will change the location of that offset. So it's one of those weird things that you just have to play with. This is a very simple program, so that's not really going to happen here. So let's do this. Okay, so I have my stuff. And I will manually give it some arguments. You can see that, if I just wanted to crash it, maybe that's a good start. Let's say that you haven't even gotten to this stage. You could use a fuzzer, and there's a lot of fuzzers out there, or you could just write a Python script. That's usually what I do. Just write a little Python script and say, all right, run this. See if I can get it to crash. So just so we can say we've done it once, I'm going to give it a whole bunch of A's. More than enough. And I'll run it again. So you have to restart. I know that. Program exited anyway. I'm just going to say run it. And run it again. And run it again. And notice it said access violation when executing 41414141. Right? That is the ASCII value for A. So I obviously overwrote it. So I'm like, whoo, found a flaw. Step 1, I crashed it. Right? And that's easy. Now, I can think back to many years ago when I first learned about stack buffer overflows. I was a developer, I wasn't a security guy. And I'm like, you can crash my program. Ooh, so what? I was very naive back then. I didn't realize, you can do a lot. The so what, there's a lot to the so what part. There's a lot of things you can do beyond just crashing the program. Now, sometimes, especially if you're dealing with a modern version of Windows or Linux, it's hard to do a lot. past just crashing. Sometimes that's enough. You're doing a DOS attack of some sort, and do denial of service. At least you can do that. Okay. So how can I figure this out? I could do this manually. Let me do it that way. I'll just do this. 4 A's, 4 B's. We'll just start with that. And see if that's enough. Obviously, some programs you might need a couple thousand characters, so it'll be a little harder to do that. So I'm just going to run it and see if I can get it to crash. Okay, and it did. And notice what it told me. It said 494848. So how far along is that? So 494848. Well, that's not too far into it. I can see how far I've gone right here. And I can do a little bit of math. So since I didn't have to go too far, now there's some other folks out there, and they'll say, oh, well, you can run this script, and you can have all these random non-repeating numbers, and you can do all this stuff. And, sometimes that's just too much work. So let's try to make it simple. Now, here's one thing I will warn you about. When you're doing stuff like this, where you're doing it on the command line, instead of over the network, you can run into issues where some of these are funny characters, like a backspace, or a null character, or some other control character, and it's just like, it'll mess you up. Control C, something like that. It says, oh, I don't want to run this program at all. You hit Control C. So it seems to me like I have 1, 2 plus 4, 6, 10, 14, 18, 22, 26, 20, 30. Right, 30, and then we were what? Halfway there? 49, 49, 48. So let's say, is it 30 or 34? Well, let's try 30. And see if I'm right. Now, often, I'll just write a little Python script for this. Let's see if we can avoid using Python. Not that I don't like using Python. Who doesn't know Python in here? Oh, I guess we could have used it. How do you do it with Python? A times 30 plus your string. But just for grants, let's do it one time manually. Let's see if I can count to 30. I think that was 30. And then I'm going to write B, C, D, E. We'll see if I was off by 4 or not. It's been a while since I ran this program, so I don't remember. All right. So what does it say? My address was 42434465. I'm off. I'm a little bit off, aren't I? Because I want it to be, it should say, is that 4? It is a 4. 42. I'm sorry. No, I'm not off. It just looked funny on this display. It says 42434445. So I was exactly right. I had 30, doesn't matter what they are, bytes, followed by the 3 bytes I needed. So now what? The answer to now what depends on the operating system that I'm running. If I'm running Windows XP, I'm almost done. If I'm running Windows XP, what can I do? I can say, well, what is my stack address? I will take that stack address and I will put that next. So here it is. And I want to use this address, 28FEA0. I want to put that in there. How the heck do I do that by entering it on the command line? That's a little bit hard, isn't it? It's a little bit rough to do. Again, sometimes this is harder to do on the command line. After that, I want to insert some shell code. Well, let me have a look here in my Windows system. And I want to look at some of my Python scripts. So I'm going to go ahead and open up Terminal. And I'll notice that I have a few Python scripts. And I see one called chainy format, okay, fuzzy, one called testy. Let's have a look at fuzzy. So basically, how does fuzzy work? I just send it a bunch of characters. I call my program buffer overflow, and I give it a bunch of parameters, and then I do some math later. Right? So this is the other way we could have gone. You might say, well, what do you mean? What I could have done is I could have said, all right, I want to run Python and I'll run fuzzy.py. It says, all right, this program crashed. I look at the details. It gives me my offset. It says C2, C1, C0, BF. Right. Again, it's a little end. So this is basically BF, C0, C1, C2. That's how it's going to appear. If I look at my script, My script started at A1. So what I need to know is, what is BF minus A1? What's my offset? I could use my calculator. In hex mode. So what is BF minus A1? It says that is in fact 1E.
Can you slide that a little bit?
Oh, sorry.
It's off the X.
The joys of doing all this stuff. And if I convert that 1E to decimal, is it in fact 30? Right? So this is another way, more scientific way I could find it. So you guys understand how we just did this? Right. So we said, all right, 30 characters. Now, what can I do from here? From here, I could take this script and I could modify it a little bit. And I think this is the one I want. And what I'm going to do is build this parameter. I'll say this is the parameter, 30 A's. And then to this, I can add a certain value. And then I might add a bunch of hex 9 zeros. Why do I like hex 9 zeros? That is a what? It's a NOP. No operation.
Just skip over it.
So, what does a NOP do?
Gets you where you want.
Get you where you want. NOPs are used for padding. Like, legitimately used for padding. So, if you're into forensics and you look at things like, let's say, it's a master boot record or a volume boot record kind of file system, you'll see on a volume boot record. Yeah, volume boot record. First 3 bytes are a jump instruction. It'll say E9, I think, and then how many bytes to jump ahead. What's called a short jump, and the next byte will be 90. Not. It's just a buffer placeholder. So in exploitation of software, we use knobs all the time. And here's what we use them for. Sometimes you don't have very fine control over where you're going to redirect something. Now, we're not talking about heap problems today, but if you look at heap problems, you might do what's called heap spraying, where you have, let's say, a web browser like IE has lots of problems, and some of them you can exploit using heap spraying. So what you do is you just fill the RAM. So that way when you redirect it, you're probably going to get your bad code. So what you do is you put a bunch of NOPs in there, and then you put your bad code. And then a bunch more NOPs, then your bad code again. You just repeat it over and over and over again. Now, when you load up Metasploit, you'll notice it comes up and says, I have this many exploits, this many payloads. If you look, it says I have this many NOPs. Because a lot of intrusion detection systems are like, why is my memory filling up with hex code 90? This is not normal. So what they do is they have alternatives that also do nothing, but that way you have some variety. And it makes it harder for someone to detect what you're doing. That's what we call a NOP sled. Sometimes people call it NOP slide or sled, I've heard both. And the idea is this. If you're a little bit off, you'll still get to your shellcode. So I add a NOP sled, and then I add my shellcode right here. And this is kind of the general format for an exploit. Now, I'm going to go ahead and run this. Now this will run it, and in this case, it actually is going to run it in the immunity debugger. Because immunity allows me to run immunity and then pass it a program to run it. By the way, I can also attach to a process. So if you look at the file menu in immunity, there's an attach option. If I have a daemon or some other system process that's already running, I can just attach to it and debug it. And there's some things you can't just launch it easy from the command line. This is another option that we have. Okay. So I'm going to close this because I'm going to reopen it here in a second. And now I'm going to run this little test script.
Why? Test.
There you go. Tab completion is your friend. I always tell my students that when I see them. It's so painful watching them. Even in an advanced class, I'm like, we had the need to do something on command because the tool we had it's called Active Disk Editor. It's a great tool, but some other classes were running it and they were pointing toward disk images that weren't accessible to these students because they were mounted under other students' drives. And they also didn't untick the box that says, "Would you load the things I was working on last?" So they try to run it, and the tool would be like, "I can't open this," and it would close. And it was really bad because they were all trying to take a test. Well, I found a command line switch for this tool that would fix that problem. But these are like seniors, and I had to step by step CD to really? Okay. So here we go. And it says I'm running it. I'm going to hit F9. And it says single step event at NTDLL, blah, 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 blah. Do you want to pass this to your program or not? So basically, here's what happened. My program crashed. Why did my program crash? My program crashed because of this. Let's see. Notice how I gave it this bad value, dead beef. Okay, I told it dead beef. Why is that a problem? Well, the problem is this. I can't give it the stack address directly. And here's why I can't do that. What does this address start with? 00. What is that? It's a null terminator. You see the problem? If I try to copy a string, it contains that value. It goes, oh, that's a null. We're done. Stops copying. So on the command line especially, this is a bit of a problem. And this actually is good timing because this is a
Because IBM embedded have to work very closely on anything that has to do with HPC.
Squirrel.
HPC
Thank goodness Laura's going over.
All right, we'll go ahead and start back. Real quick before we get back into this, when you look at a tool like Metasploit and you see an exploit, often it'll say, this is how much space I have for your shellcode. Right? I only have 50 bytes. And you might say, oh, that's not a lot. And you start looking at some of these shellcodes, and you find you can do a lot with 50 bytes. Sometimes you can do a lot with 30 bytes. You'd be amazed. So if I go back to Metasploit and I say, oh, okay, maybe eventually I want to develop an exploit based on this flaw that I just found. When I develop that, I will say, this is how many bytes are available. One of the reasons for that could be that, we said, if we go back a few slides, we said that often the standard thing you do is you overwrite that return address, and immediately after the return address, you put your shellcode. Nobody says you can't put your shellcode before it. And what is the good advantage of doing that beforehand? Well, we said that the address that we have is going to start with 00, and that's our problem. That's a null terminator. Well, guess what? Am I going to write a 00 when I call stir copy? I am. Right? It's going to put a null terminator in there, and it's little ended. So in memory, this address is stored as F0FF2800. I'm golden now, right? You see what I'm saying here? If I have enough space, I can put that shellcode before the return address, and I can say, go here. Stop. If I don't have some of the protections we're going to talk about here in a little bit. So that's one method. There is another method that you can use, and it's something called jump ESP. And the idea is this. I just loaded this program again. You'll notice right here I'm in NTDLL. What are the memory addresses for NTDLL look like? Hey, there's not a leading null byte, is there? There's more than just this one DLL that's loaded. So what I could do is I can go here to view, and I can say view memory, please, and I can look at all these different memory segments. I apologize that it's microscopic, but I will see things like kernel 32, MSVCRT, that's the Microsoft Visual C runtime library, NTDLL, and here's what you want to do. If you look at each of these sections, there's a text section. I don't want to get into all those assembly details, but the text section has your code in it. I can search for an instruction to jump to ESP. Jump or call ESP. I don't really care if it's a call or a jump, as long as I get there. So what I could do is something like this. Let's just say NTDLL, I've already displayed it. And now I can search. Let's see if I can remember how to do this. I want to find a command. I'll search for a command. And the command, hey, guess what? It's already in here in my buffer. Jump GMP ESP. Fine. Now I have an address. So I take this address, and this is the address that I'm going to put into my location. So if I go back to my testing, you'll notice, I think I actually have this exact address. Okay, it's not this one, but it's a different one. I think this was a different DLL. That's all. There's more than one DLL that you could use. But basically, all you need to do is say, that's my return address. And that's the one you poke in there, and it goes back to where your stack is. It's a beautiful thing. And that works very well. That is useful, definitely for Windows. Some versions of Linux, it might also be relevant. Now, it turns out when you get into 64-bit, it's totally different. So the biggest thing is, so far, let's just check and make sure we kind of figured out how all this stuff works. What do I need? I need to have something where I stupidly let the user input code or input data into a part of my program where I'm not checking stuff. And that results in something being passed to a function, and usually something like stir copy is called, or something else like that, that overwrites a local variable somewhere, that ultimately overwrites a return address. And I can do bad things. So I can do a lot more than crash a program, can't I? A lot more. Okay. Now let's talk about some of these complications. Go back here. Stack protections. How do I make this difficult for you? Well, there are a couple of standard schemes for this. The first one we're going to talk about is a non-executable stack. Sometimes you'll hear people talk about the NX bit, different memory areas in your Intel system can be flagged with permissions. Read, write, execute. Standard Linux or Unix permissions. So you can set the don't execute bit to a memory segment, and then that's a problem. You can't just run the stack if it's been marked as non-executable. Another thing you can do is you might have a system that uses address space layout randomization. ASLR. Now it's not always in the same place. I can't just put a fixed address in there. It doesn't work. Yes, sir?
Was that around before Spectre and Meltdown?
Yes.
Or was that, okay. But that's one of the things that prevents it.
We'll talk a little bit more about this in detail in just a little bit. And then we have something called stack canaries. So, non-executable stacks. Again, read, write, execute flags. The stack should not be executable. Windows XP, guess what? Yeah, go right ahead. And honestly, you shouldn't have a chunk of memory that is writable and executable. It's okay to be writable and readable, but not executable. But you shouldn't be writable and executable at the same time. That can lead to issues. So, if my stack is not executable, I can't just put my shellcode in the stack and run it, can I? I got to do something differently. In Windows XP, Service Pack 2, they introduced this non-executable stack. Being Microsoft, they had to give it its own special name. And it's called Data Execution Prevention, DEP. And a big part of it is a non-executable stack. Guess what? Not enabled by default. Later versions of Windows, this might be enabled. Sometimes it's enabled for system processes, but not for your everyday programs. You might say, why is that? Because people get unhappy when their programs don't work anymore. People are like, oh, my programs don't work, but you're safer. It's like, I want to be safe when I fly. You stay on the ground, you're safe now, but you're not doing what you wanted. Well, actually, you're not going to be as safe because you're going to drive, and that's a heck of a lot more dangerous than flying the airlines, isn't it? Anyone afraid to fly in here? I'll take you flying sometime, then it'll really be afraid. Then you'll like, those airlines are awesome. What do you want?
My father used to fly.
You want to fly a chopper and really get the fear going, or you want to go in an airplane? You can do either one.
We did a little twin engine, and it seemed like every nut and bolt was just a little bit loose because all of it wiggled.
Oh well, definitely the chopper then, because everything wiggles on a chopper. Right? In fact, I remember one day I was watching someone else. They came in their chopper, and I'm like, wow. It's a good thing that I can't see the tail when I'm in the chopper, because they're sitting on the ground just getting ready to shut it down, and that whole tail is going like this. I'm like, oh, but I can't see these things. You kind of feel it. I'm like, boy, these little choppers especially. You get a little gust of wind, up on your side. Yeah, it usually goes back. Usually. Like, hey, that's weird. Huh? Back to normal. Okay. Other things that can be done that make your life difficult. ASLR, Address Space Layout Randomization. Here's what gets localized. This is for Windows. Linux is slightly different. They will randomize the heap. What's the heap? We haven't talked about that. You're correct, we have not. But the heap is the other way of allocating memory. We said stack variables are sometimes called automatic variables. You just go, integer x. This is okay. Here you go. Well, that's not the best way to allocate memory if I have a lot of memory to allocate. In fact, with older systems and compilers, the stack had a fixed size. Anybody remember this? You want a 4K stack or an 8K stack, you actually have to specify this. Some microcontrollers, you still have to specify this. Microcontrollers is like, this one has 16K of RAM. It's huge. So you still have to specify how much stack space you want. So the heap is just big chunks of RAM. You call a function like malloc, which just means memory allocate. And there are a bunch of related functions. In C++ or Java, you can use new. You can say this, new that. Well, not so much in Java, but in C++. You can make a huge array of stuff. And when you're creating huge items in memory, you will tend to use the heap. There are some people who are like, I just never use the stack. Problem solved. Well, I would refer you to the complete reverse engineering class, and you'll find out even when you're using the heap, there are other problems that can creep up. So just not using the stack doesn't fix this problem. And if you stay for the format string part of our little workshop today, you'll realize that, oh, there's even more things there. Okay, so it randomizes the heap, the stack, and these other things, the PEB and the TEB, the process environment block and the thread environment block. These are just structures that Windows uses to keep track of processes and threads. Do you guys know what threads are? Threads are processes inside of a process, if you will. Sometimes they're called lightweight processes. Multi-threaded programming is a beautiful thing. makes life a lot better, makes programming easier, makes programming systems more efficient. I remember some years ago, I was at Purdue studying physics, not computer science, and I was taking a few classes just for grins. I was taking an algorithms class, people looking around like, who's this guy? They're all seniors. They put it off to the last semester there because they didn't want to take this class. I haven't seen you before, and I've been here for 4 years. Who the hell are you? I'm like, oh, I'm a grad student here in physics. I'm just taking this for fun. I'm like, for fun? What? And I remember an OS class I took, and it was taught by a professor. He had just got his PhD in computer science. And someone asked him about threading. And he said, I could only give you hand-waving arguments about threading. This is like a research topic. And blah, blah. And I'm like, at the time, there was an operating system called OS2. Have you ever heard of it? Yeah. Everyone ran it. It was awesome, but, you know, I was talking to the Red Hat guys the other day. I'm like, I just hope that IBM doesn't do to Red Hat what it did to OS2 and some other things. I know this is being recorded, so I'm not going to say too much more about IBM, but sometimes they take successful ventures and make them a little less successful. Hopefully that doesn't happen. You know, OS2 had been out for years at that point, and people were running OS2. I'm like, hand-waving argument. This guy is not in touch with reality. You got a shipping operating system out there. OS2 programmers are like physicists. Everybody wants to hire them, but not to program OS2. Well, definitely not today. But even back when you could still buy OS2. But why do people want to hire OS2 programmers? Because they understood things like object-oriented programming, multi-threaded programming better than a lot of other people because they've been doing it a long time. So this was introduced in Vista. Dun, dun, dun! Not enabled by default. The other thing you should know is the 32-bit implementations are not the best. What does that mean? There's only a few bits that you can randomize in this situation. You got 32 bits, you're like, oh, it's 32 bits. No, because of other limitations, you really have about 12 bits that you can play with. And even then, it's somewhat predictable. Yeah, there's 4 places it might land. So I'm going to guess. And if I run something enough times, just guessing, I don't get it. So there are some things that you can do. And then the other one is stack canaries. So what is a stack canary? It's a known value that you put on the stack. Let's start with the canary. What is a canary? It's kind of bird. What is a canary used for? Or used to be used for? Well, in this area, still coal mining. Coal mining. So in the coal mines, you know, there's none of those around here, right? What do you use a canary for in your coal mine?
To see if it dies.
To see if it dies, right? Even today, in places where they don't have coal mining, if you go to a water treatment plant, they often have some fish. They have some fish that are very sensitive to certain impurities in water. And they watch those fish. When those fish die, they shut off the water supply. Something bad is happening. People are going to die. Apparently they don't do stuff like that around here. I heard some stories last night about some incidents and some chemicals being dumped, and I think people coming to HackerCon and taking a shower at this hotel and ended up with red and stuff like that. But so a canary is just there to tell you, hey, something's wrong. In aviation, sometimes they'll talk about canary, or actually a parrot. Transponder just says, hey, I'm over here. It's kind of like a canary. different kinds of canaries you can have. So canary is used to detect some sort of tenant. So you can have a terminator canary. I'm sorry, terminator. If you want to get to the chopper, we'll do that later. Scare you in the chopper. I don't think I can rent a chopper though. Come to BloomCon. We'll get you to the chopper after BloomCon. By the way, BloomCon, March 29th through 31st, coming up, Bloomsburg, Pennsylvania. We'd love to have you. $20 or tickets right now, $20. If you're a student at Marshall, talk to Bill Gardner, and I told him I'd hook you up with some tickets. So a terminator canary is just there to prevent you from putting stuff on the stack. And then there's a random canary. It doesn't prevent stir copy and things like it from working, but it's detected. It's a little bit harder to deal with. Microsoft Visual Studio introduced this ability way back then. You have this GS switch, enables canaries. It was introduced in 2003 and was not enabled until 2005. So that's a stack. So how do I mitigate some of these things? ASLR. I can use a few different techniques in order to mitigate this. So let's go back to what we just did. We used a jump ESP instruction. We found it in a library. So what am I going to do? Now the libraries are loaded in random places. They're not loaded in the same place every time. There are a couple of solutions to this problem. One of them is to use what in the Linux world is called a PLT, procedural linkage table. It's called something slightly different. In Windows, I honestly don't remember what it was. You don't care. Okay? And here's the way it works. Whenever I have a library function that's being called in my program, in the space where I have my main program, it will create this table that says, I want to call stir copy in MSVCRT. Where is it? So instead of calling stir copy directly, what happens is it creates this table in memory, and then when it loads everything in memory, it says, let me fix this up for you. Let me say, for this version of this program that ran right now, this is where I can find stir copy. So you can attack that. You can read the table out. Read the table, and then you're like, oh, now I know it. I know what it is, now I can do some other stuff. It's a little complicated, but you can do it. You can also do something called return-oriented programming, or ROP, or ROPE, depending on who you ask. And we'll get into that in a little bit. Or you can brute force it. We said that there are only a few choices that are available, and you can brute force your way into it. So you might say, well, how would I do that? If I know for this version of this DLL what the offset is to stir copy, that never changes. The base address where the DLL gets loaded is going to change. The offset never changes. Guess what I can do? I can search for that DLL. And I can say, oh, I went to this offset. This looks like the start of stir copy. Great. Problem solved. So let's talk a little bit about rope, return-oriented program execution, if you will. How does this work? You build the function you want. So what you do is you look for code immediately before a return instruction. And you can say, this is how many bytes back from the return I want to go. And you say, oh, I wanted to load the value 4 into EAX. Or I wanted to add 4 to EAX. Or I wanted to jump to ESP or EDX or whatever. I wanted to do something. I want to build the function that I want. And so I build it using what we call gadgets. A gadget is just a couple of assembly instructions that precede a return. So I look through the code, and what code do I want to look through? I probably want to look through the library code. Why not the actual program? No byte in the address. Library code, no byte. Unless you pick badly, something that just happens to have an embedded null somewhere in that address. I'll find another one. I'll use that one. So what you do is you use one of these tools, and I've listed a couple here. One of them is called RP++. It's called RopeMe, ROP Gadget. RP++ is my preferred tool. I just use that tool, and it'll search through a program, and it'll say, all right, well, let me look through all the different memory segments and look for return addresses and 3 instructions, up to 3 instructions before that. And it'll tell you, here's all these places, and here's what is there. These 3 instructions were there. Great. And you just build a program like that. So what do? You put on your stack a lot of stuff sometimes. So you build this whole string of function calls. It's like you're going to call it here, you're going to return. You're going to call it here, and you're going to return. Here, return, here, return, here, return, here, return. Until you get what you want. Now, this is going to be a little hard if you don't know assembly. If you don't know assembly very well, it's going to be kind of difficult. It's like, I don't know this language, but I want to build programs in it. If you really don't know assembly, then a tool like RP++ is your best bet. There's a little link here. You can get it on GitHub. You can manually search through code. Sometimes you'll do a little bit better than these automated tools. Sounds like a parrot, not canary, is making a little noise today. Yesterday, she was really quiet most of the day, and then in the evening, she started getting really loud. I was trying to talk to my kids, like, telling my son, like, you hear that meowing? That's actually not a cat. It's a bird. All right, so you can manually do this stuff as well. If you're going to do it manually, then you're going to need a little bit better understanding. If you're doing this on Linux, you can use a tool like objdump-d, and it'll disassemble things. There are some caveats when you do static disassemblies like that. If you have self-modifying code, it can be a little bit complicated. All right, a little bit about stack canaries. It's just a value you put on the stack. It's not a return address or an argument. And what happens if you have stack canaries, it'll put a little preamble, a little epilogue onto every function call. Or it's going to say, oh, you're calling this function, let me put this stuff on the stack, and then when I return, let me make sure you didn't screw it up. So this is a compiler function. we're talking about non-executable stacks. That is an operating system function. So this is a compiler protection. And again, two common types, terminator and random. So what's an example of a terminator? This is not the only terminator you could use, but you know, it's probably this rearranged somehow, honestly. 000A, 0D, FF. So what happens? Every one of these bytes will cause an issue for some program, some function. The null byte, stir copy and related functions will go, whoa, null byte, I'm done. I'm going to stop. Right. Gets, get string, and similar functions are blocked by a new line. Now, in good operating systems, a new line is what? Hex 0A? Or is it 0D? I want to say 0A. But, and then there's Windows. You probably encountered this before. You're looking at a text file. You're like, why does every line go off into infinity? And it's because it was edited on something other than Windows. DOS and Windows are the only operating systems that do carriage return line feed. Everyone else just says new line. Done. So those two characters are going to cause problems for things like gets. It's like, oh, you hit enter. Basic. And what about FF? File functions will interpret that as an end of file marker. So, you know, there's something for everybody. It's an equal opportunity offender, if you will. Some people are like that, especially people in InfoSec. It's a goal. I try to offend everybody equally. Now, here's what's wrong with this. If it's a static value, can I search for a static value? Yeah, that's pretty easy. Can I overwrite the static value with itself? Yeah, I could possibly do that. Right? Again, think back to the earlier discussion we had. We said, if I have a problem where I can't use something like jump ESP, I have enough space, I can put my shellcode on the stack. Right? I can possibly put my shellcode on the stack and overwrite the stat canary with the stat canary. Done. In fact, when Microsoft first added this protection, they made it worse. They made it easier to exploit programs compiled with their compiler until they fixed it. Okay, random canary. Doesn't stop things, it just detects. It's like that LifeLock commercial. Like, they used to run in this. You guys know what I'm talking about? It's like the guard at the bank. You are being robbed. Why don't you do something? I only detect. I don't stop things. Right? That's a random canary. You are being hacked. Okay, thank you. Thank you for telling me. I guess it's intrusion detection, not prevention. That's a topic for another day. A lot harder to thwart, though, isn't it? I don't have a static value. So now if I'm trying to put my code in that area, I'm trying to say, oh, I'm not gonna overwrite this. You know, I'm gonna put my shellcode in there. It's gonna be great. And you're like, no, it isn't. It's not gonna be so great. So that's a random canary. So how do you attack terminator canary? Overwrite up to the canary. And again, If the stack is executable, this is the easiest. If it's not executable, not strictly required, but still, you could do it. Random canary. Pretty hard in Linux, just based on the way that it works. A little bit easier in Windows, still not terribly easy. Some things you can do. Remember we said at the start of today that sometimes you can crash a program. You're like, okay, fairly easy to do. Windows has something called an instruction exception handler. Any Windows programmers in here? Anybody ever heard of these before just now? A little bit? Yeah, heard of it. So it's sort of like faking exception handling. Exception handling is a function of C++ and Java and some other languages. And at the operating system level, they're essentially faking that. With structured exception handling. And I could modify the stack and intentionally cause it to raise an exception. And if I have somehow managed to change the exception handler, I'm golden. Now I have an exploit, right? I created an exception. I've already, infiltrated your exception handler, if you will. And you go to my Trojan or altered exception handler in Bethington. You could try to brute force it, but yeah, good luck with that. It's a 32-bit value. That's a lot of bits. We talked about the ASLR mitigation. We said, yeah, it's kind of 12 bits, maybe a little bit less that you're effectively going to change. So, this is a lot harder to get right. All right, so I just want to give you a quick summary of at least the stack overflow stuff. So if the user has control of a variable, it's passed to a function, you could have an exploit, possibly. Overflowing that variable can overwrite other stuff, including that return address, thus redirect your program. Several protections that you might find in modern versions of Windows or Linux. ASLR, protection provided by the OS. Non-executable stack is a function that you can have provided by the compiler, and stack canaries are also provided by the compiler. So, real quick here, we hit the correct thing. Go back. Wow, I just barely tapped the power button. I know it's about lunchtime. I wanted to kind of finish up, and then, after lunch, we'll talk about format strings. Get my laptop here a second. Wake up, laptop. And if it takes too long, then we might just have an early one. Why is it so easy to go to sleep and not to wake up? Come on.
Usually have the opposite problem.
Yeah, especially when you're traveling, right? You're always like, I can't go to sleep. And I have the most horrible room, too. It's like right by the elevator. I mean, right by the elevator, like, there's a rack or whatever, closet, and right behind it is the elevator. It's like the elevator's like literally right there. And you have to walk by it to go to the bathroom. And it's horrible. It's just absolutely. I'm really hoping this is going to go back to where it was. If not, we'll take that early. I just wanted to show you real quick, when you look at those memory sections, it will tell you, hey, look, these are the protections on this memory section. And you can see that the stack is not executable. Yeah, it totally did that to me, didn't it? Yeah, it sure did. After lunch,
You're recording?
Only recording.
Oh God, nobody ever told me.
a bunch of traffic.
Came out morning.
I just walked around campus for about a half hour
You're recording also though, right?
with
Yeah,
my
I was recording
laptop.
also. I recorded in
And
stream.
here's the crazy thing.
I got it. 'Cause I was
Nobody
filming like Derby
challenged
just
me.
streaming.
I walked around
So-
campus, laptop. I got multiple alpha
Okay, so
adapters.
we should be
Big
good.
antennas,
So
just walking around campus, walking around the quad, walking to different buildings, and I got, I don't even know how many hundreds of clients and access points within a half hour. But that's a tool that they have available. It's a free tool for visualizing some large dumps from aircraft. Web application pen testing class, network pen testing class, PowerShell, real world pen testing, Windows forensics, log file analysis, data science, and the list goes on and on. OSINT, if you like to do OSINT challenges, wireless monitoring. Let's see if there's something new I didn't even know about. VoIP, red teaming, rootkits, reverse engineering. It says that this class that this stuff is based on is an ongoing class. It's actually done. It's just that they haven't completely uploaded it and called it done yet, which they have done apparently with my Linux class. Okay, well now it's 1 o'clock, so we can go ahead and get back to our class. I just wanted to show you that real quick. So this morning we talked about stack buffer overflows, well-known flaws, been there forever. And now I want to talk a little bit about something called format string error. So what is a format string error? A format string is something you pass to several functions, a family of functions. The typical example of these functions is printf. We talked about this briefly this morning. We said with printf, you can give it an argument. And the first argument can be a format string that says, here's how I would like you to print out the other things I'm going to pass to you. And it is very powerful. You can print things out in an exact way. There are related functions like fprintf and sprintf that do about the same thing. But normally we talk about printf, but it could be a different related function. Now, here's where the problem comes in. Some programs, or some programmers, will call this function assuming there's only one argument that you pass in. And I'll admit it, I do this all the time because I'm lazy. Here's where the problem lies. If the user can control the input, again, just like stack buffer overflows, user controls input, there's some sort of a flaw in the program, possible exploit. So if I'm trying to say printf my variable, but the user controls my variable, some bad things can happen. Either I can leak information, or I can cause a program to crash. What's the simple fix? You say printf, give it a format string every time. You say %s, that's safe. Anything can be represented as a string pretty much. Your variable, and this problem completely goes away. Problem solved. So, you know, that's like all you have to do. All you have to do is that one simple thing. So we'll go ahead and do this. I have a few simple functions, and for now at least, I'm just going to stick with my Linux system. I mean, you can compile the ones that are on the Windows image as well. Let me just do this one. Okay, so I have this program. It's called format.c. Let's see if it compiles. I think I have it compiled. All right, thankfully I have it compiled. So GCC format C -o format. Okay. It compiled and it made my program. Notice what it did. How much do you love Linux and the open source community? Warning! Format! Not a string literal, and no format arguments. Printf, argv1. It just warned me, hey, you could have a problem. And it even tells me this is how, if you wanted to turn this warning off, you can turn it off. But by default, it's enabled. So if I redo this, let's just go ahead and give it this -w format. Still warned me, actually. Huh. Oh, you know what? It's because I didn't say it's -w minus. No. Okay, well anyway, there is a way to turn it off, I just can't remember what it is. So let's look at my simple program. Go ahead and bring it up in Ghead. This doesn't really do much. Got my standard includes here, standard lib, standard IO. Let me make this a little larger for you. All right, now we can read it. So I include my standard lib, standard IO. I have my main function, int main argc, argv. And it says this function, or this program prints what the user inputs. You say if argc is greater than 1, print whatever you pass. That's it. Pretty simple, right? So I can run it. Format. Hello. Let me print it out hello. I can say hello world. Doesn't do what I expect. Why not? Because world is argv2, not argv1. You could fix that by using quotes. I could even add a new line. So, didn't interpret the new line, but there are other reasons for that. Okay, so that is my super simple function. Oh, what's wrong with that? Everything seems great still. Easy little program, nothing bad could ever happen, right? Well, let me do this. Let me run it, and instead of saying format, I'm going to say %. Yes. Well, that's interesting. What did it do? Huh. How many people thought it was going to crash? They said %s. Seems like it should crash, right? I didn't give it any arguments. So where did it get the arguments for printf? I didn't give it any. On the stack, right? You called printf, and there was stuff on the stack. It appears as though randomly it had %s. It said, oh, the next thing on the stack is the pointer to this little string. Okay, well, I bet I could get it to crash. I'm going to give it %s. I'm going to give it a whole bunch of %s. Okay, now I got it to crash. It still printed out my stuff, and then it said segmentation fault, which is Unix and Linux speak for, yeah, I died. If you have a system and it's configured a certain way, it'll actually come up and it'll say segmentation fault, core dumped, and it'll give you a core file. In this case, I don't have it set up like that. All right, so I can crash this program. Step 1. We found that with Windows and stack buffer overflows, that's fairly easy to do. Even if you have all these protections in place, you can still cause it to crash. So I could DOS this ever so important program here that just prints out what people type. Well, let me do this since I have this thing connected to the internet. Let's say printf format specified. Let's say, what are these format specifiers? Well, I have %c, a character, okay, %o, octal number, %s, string, pretty common, %u, an unsigned integer, %x, a number in hex, says 6 more rows. Let's see, what are the other rows? I have unsigned numbers, hex numbers. I can print a %sign. Right. So the first thing I went to is okay, but it doesn't have everything that I would want. That's okay. We'll get back to that. Okay. So what if I, instead of using all these %s's, maybe I'll just do 1%s. Let's say %x, x, %x. Did it segfault this time? It did not. Why not?
Last time you were asking for a string, and what it had wasn't a string.
Correct. The first thing was a string. And the things after it weren't easily interpreted as a string. But %x is a hex number. if I am reading things off of my stack, which what I'm doing, can I interpret most anything as a hex number? Yeah. So now what I'm doing is I am reading my stack 1 4-byte integer at a time, since it's 32-bit Windows, or 32-bit Linux. Actually, I shouldn't say 32-bit, because I just realized I forgot to do something. I forgot to compile it as a 32-bit app. It's not necessarily a bad thing that I forgot this, and here's why it's not bad. Format strings, we said they are agnostic to operating systems, aren't they? And that means that unlike stack buffer overflows, which if you did 64-bit Windows and you look at stack buffer overflows, you would find those are a lot harder to exploit. Much, much harder. These are just as easy to exploit all the time. It doesn't matter. It doesn't matter if it's Windows or Linux, if it's 32-bit or 64-bit. Now, if you're wondering why is 64-bit harder to exploit, think about the things we talked about this morning. The address space is much larger. If I randomize the address space, now can you find stuff? Let's say I only have 50 bits to randomize. That's a lot of bits. You're going to be brute forcing for a long time. That's number one. Number two, what you'll find is that for 64-bit versions of operating systems, often they don't put things on the stack so much. They use registers instead. So they'll use what we call fast decal or fast call, where you might put, as much as you can, you put things in the registers. Why do you do that? It's a lot faster. So they will just say, okay, we're going to use the registers to pass all these parameters. If you look at ARM, by the way, guess what? That's what they do. And ARM has a special register for the return address. You call it function. It's not necessarily on the stack at all. So ARM exploitation can be a lot more difficult than Windows. Also, people don't understand it as well. And ARM assembly is weird. And sometimes ARM, you're talking about Java machines, and there are certain ARM compilers which will natively interpret Java bytecode, which is an awesome feature. It does make your life a little bit harder sometimes. Okay. So I was able to print out what's on my stack. Now, if I rerun this, do I get the exact same results? Survey says, no. What does that tell me? I'm using ASLR, right? Address space layout randomization. Not surprising, this is 64-bit Linux. So yeah, it's doing that. How long has Linux been doing this? I don't even know how long. Like, over a decade. I remember when Vista came out, many years late, and everyone's like, oh, it's got this feature, and it's got this feature, and it's just so awesome. One of the Linux magazines put out an article, and they're like, here's all these highly touted features of Windows Vista, and here's how long they've been in Linux. And some of them were over a decade. They've already been in Linux for that long. Okay. Let's go back, and I'm going to run up my virtual machine. Let's see if this is any different from Windows. now it's Windows is mad at me, right? When I just barely bumped that power button and it didn't, go to sleep, and it just, I'm just going to shut it down. Of course, power it off my Windows virtual machine. One of my virtual machine tips is always full screen your virtual machine. I don't know how many times I'll have students who are like, I can't find this file I downloaded. It's like, did you download it to your VirtualBox or did you download it to your host machine? But if you don't full screen the virtualized machine, the guest, that tends to happen a lot. All right, let me go ahead and open this format program. Same program. We build it. By the way, we haven't used it, but there is a basic debugger built into this IDE as well. Okay. Go ahead and run this. Notice I got slightly different results. Why is that? Well, it's a different operating system. It's also 32-bit instead of 64-bit, at least. Can we verify that? Yes. 32-bit release build. And if I just say %x a few times, okay? Now, what do you notice about this?
Sequential.
It's not exactly the same. So it's not exactly the same because I'm using address space layout randomization on my Windows 7 box. There is a way to turn it off. I will leave it as an exercise to you guys to figure it out. Just Google it. You'll probably find it for you. But you can go into the settings and you can say, I want to turn it off for everything or just for system processes. You might say, why is there not a everything but system processes? I don't think that's an option, if I remember correctly, because that's a security problem. Microsoft can control their DLLs. So they can make sure that their DLLs still work, even if they're using randomization. But they can't control your code. And that's why you can turn it on and off for various programs. Okay. So what are some of these other things that might cause additional problems? And here is an additional issue. So we already saw, what can I do? I can just keep on going, and I can dump huge chunks of the stack. So can you guys see how I can leak information? Pretty easy to see that. We saw how we could crash the program. Also pretty easy to see that. Well, here's something really interesting that we can do. there is a parameter called %n. And that says nothing's printed. The corresponding argument must be a pointer to a signed int. The number of characters written so far is stored in the pointed location. This will write an integer. You might say, so what? Here's where this is about to get interesting. I want to crash this program. %n. All right, how many people think this is going to crash my program? It does. Instant. Why? %n says, I'm going to give you an address, and I would like you to write the number of characters output so far to that variable, which is a signed integer. And then there's no additional parameter. So where is it going to get the %n? It's going to get the %n off the stack. All right, is that a problem? Yeah. Because it's not going to find anything. Okay. So what can we do with a format string flaw? Crash the program? Pretty easy. We can also leak information. Do you think we could write information to memory? Yes. How do we do that? We can put a %n in there, and then that will cause whatever it thinks is the next parameter to my printf call, that memory location, whatever the heck is stored there, it'll say, let me go to that address and now go write this stuff. Wow, that's interesting. That's very interesting, isn't it? So let's run this one again. Instead of running it with all the %n, let me run some more %x's. And of course, I could use Python, right? I could use Python to generate this, or if I'm really old school, I guess I could use Perl to generate this, and I could say, let me just print out all this stuff. I can also make my life a little easier by doing this, right? Maybe putting a tab in it or something. Well, we'll just use spaces for now. Okay, so I run it again, and I'll notice that I'm getting certain changes. Why is that? Well, because my stack is moving. I can eventually find out where I'm going to be on the stack. I can move the location that's being printed out. And you're like, well, how do you do that? You change what's being put out there. Why is it doing that to me? It's just weird. I don't like that. So, for example, I could print a bunch of A's. Okay? It's just a few A's there. All right, that's being printed out. What if I give it a ton of A's? what should happen eventually, these numbers I'm printing out might be 41414141, right? So just like we had this issue with our stack buffer overflows where we had to find that offset, we went through a couple of ways that you could calculate that. You can do something similar here, where you could just adjust some token characters until you started to get that being printed out here. So that is one part of what you can do. You can just add, you know, a ton of these guys. Now, in the case of this particular program, it's not doing exactly what I want. And there's a reason for this. And it's because our program is very, very simple. And the compiler is smart. I have a command line parameter that was passed in. There's not a local variable being created here. It's just directly printing it. If I go back to my program, it just says, hey, just print it right out. Okay, well, what about, I think there were some other programs here. Let me try to open those. Format 2, let's see. All right, this one's a little different. Now, in my main, I'm going to print out 2 arguments. Okay, it's just a little different. I don't think this was the one I was really looking for. Look at it. See what okay, so here I'm going to create a local string. In this case, it's 4K long. And then I'm going to call printf on that. You might say, well, this seems kind of contrived. Yeah, it is, but at the same time, our example program before was super simple. I mean, you're not going to have anything that simple. It's like, I took something on the command line, it just did nothing else, but immediately printed it. It's probably going to be some more processing. So if I take this program and I compile it, I might have some better results. I'm actually going to shorten this a little bit because I don't feel like writing that much stuff. So we'll just say, we'll make it 30. Okay. We'll just double check this last program. This is very similar. So we'll try this one. Format 3. So I'll go out here and go ahead and build it. GCC. C. -O. Once again, it gives me a warning. And let me run it. And I'm going to be lazy. And I'm going to do this exact same thing. But now I'm going to call format 3 instead of format. And it's segfaulted. You might want to say, why did it segfault? Well, this is the other thing you'll find out when you do these kinds of things. If you go too far, it'll still segfault. Why is it still going to segfault? Oh, you know all those stack protections we talked about? Yep, we got those. We got those in Linux. So now it printed out my stuff, and then it said color. So I have some other protections in place that are kind of causing this to not do exactly what I want. If I went back to Windows, I could get this to happen a little bit easier. But here's the net of it, right? If you're really careful, you can write a value to an arbitrary place in memory. So I can say, oh, well, I figured out that here's a space in memory, and it's being pointed to. I want to overwrite it. And I can do that. And I can even somewhat select the value that's going to be there by changing these values. Now, here's some other things that I can do. I can change the length of what's being output by throwing in a bunch of constants, as I was doing here. I can also do stuff like this. %0 to 6x. I'm just randomly picking this out here. What does %0 do? Put a 0 in there. Who's like really familiar with these format strings? You all said you knew Python, right? So Python uses the same format strings pretty much. It says, leading zeros, please. I would like 26 characters for that number. So now what I've done is I'm affecting this output. How long is the output going to be? When I use the %n, I'll just use that as my last one here. It's going to write a number to pretty much the very next thing on the stack. So by carefully manipulating the length of this format string and carefully manipulating the output length and aligning things just so I can actually write a specific value to a random memory address. So you guys see what I'm saying here, or is it a little fuzzy? Does it seem like this is hard? Like if I wanted to write 42 to this exact memory address, is that maybe a little bit difficult? Yeah, it is. But at the same time, you can do it. And you can do it across operating systems. And, you know, again, like stack buffer overflows, we've known about those for decades. So we got all kinds of protection against that. What's our protection against this? Well, on Linux, you get a warning. That's your protection. On Windows, no protection. Now, one thing I did want to show you is that if I go back here to my Windows box, I'm going to add %n here. I can add a couple. I can lead with %n. And apparently, this compiler, at least, I don't know about Visual Studio, isn't supporting the %n. So it's not compliant with the standards. You might say, well, it sounds like the compiler's bad. But where's it getting printf from? When it runs that?
It's a system call, right?
Yeah, well, it's a system call, or it's a call to MS VCRT, DLL. Microsoft Visual C++ runtime. Microsoft has a non-standard implementation
Shocking.
of printf. I know, because Microsoft is so into standards and complying with standards, right? They're really great about that, complying with their own standards. So Microsoft is not compliant with the C standard. It's kind of a big deal. But I wanted to make sure that I pointed that out so that you guys know, hey, when it comes to doing this stuff on Windows, it's going to be a little different. Can you disclose information with Windows? Yes. Can you get it to write to arbitrary memory locations with this version of Windows? Apparently not easy. But of course, Linux is compliant with the standard. So here's an area where things are, I don't want to say better with Windows, but you don't have the ability to use this method to write to arbitrary RAM with Windows. But you do with Linux. Because the Linux C runtime is compliant with the standards, of course. Wouldn't not comply with the standards. That's not a very Linux type thing to do. Okay, and while I'm here in Windows, you guys were supposed to remind me about this, and nobody remembered. So I feel good that I don't have the only crappy memory in the room. Let me go ahead and open this guy back up. And I wanted to show you again, if you go to View, Memory, this is where it will show you what is the access for each of these memory areas. And you'll notice a bunch of them will say read, read, write, read and execute. None of them will say read, write, execute. Although over here it has an initial column. So initially when the program loaded, everything was writable. So this is another one of those areas. You've probably heard of self-modifying code that when you run it, it changes the code that's running. That is something, if I was going to write some malware, that I might do. It is much harder to do that with modern operating systems because of this protection. You would actually have to explicitly say, I want to make my program able to write to the text segment. Or, I guess you could tweak the permissions. It's not very easy. It's not very easy to do that. So if you're looking at malware and reverse engineering malware in ways that people will obscure that, it's much harder to obscure your code if you are targeting a modern version of Windows or Linux. All right. Well, that is pretty much what I had to talk to you guys about. Just a reminder, I did rip off most of this stuff, all of this stuff, in my class at Pen Tester Academy, with permission.
With permission.
It's being recorded with permission. I have permission, but just FYI, I kind of walked you guys through that over lunch a little bit. A lot of good resources there. So, thanks for your time. Enjoy the rest of the conference.